Okay, welcome back, students. So we will pick up in this segment by continuing with the elevation that we started with in the previous segment. And we would have created the walls with their openings, but no roof on top of the building. So we want to now add the roof on top of the building. And because it's a gable roof, not a gable roof, rather a hip roof that we had done in plan, we're going to be seeing this portion of the building showing the hip end and this section over here showing the same thing but sideways. And if you look from the right, this line that is slant up here in the right elevation, that will be the triangular portion up here, and the side here now would be the side of that hip roof. So we're going to be using a slope of 27 degrees, which is at a pitch of 1612, which is called quarter pitch. So I need to discuss with you now what we know as what we call roof pitches, the slope from typical pitches. So let me jump to that. Let's talk about roof pitches and some typical factors that could influence the pitch of your roof. I have listed 7 here, or 6 rather. The list is not exhaustive, but are just a few I want to discuss. So we would say that geographical location would be an indication. My battery is running low, so let me just. All right, so there are 6 factors that we're going to be focusing on. Geographical location. If you notice on the right of the screen here, I have the eastern part of our Jamaica map. And we're looking at some parishes that are on the northeast side of the island, such as on the east as well. So St. Mary, Portland, and the St. Thomas. When we normally get hurricanes coming into the island, coming onto the island, usually it's coming off the eastern coast of Africa. So you end up with the northeast radiance. And the side of the island that would get hit first would normally be like St. Mary, Portland, and St. Thomas. So what that is telling us is since those areas are impacted first, persons who live on that side of the island should really consider creating roofs that are a little steeper so that the wind does not get underneath the eave of the roof and lift it off easily. So you would want to be thinking about, instead of creating your roof too shallow like that, you would want to create it a little steeper so the wind doesn't get underneath it easily and lift the roof off. So geographical location would be a factor. You could also have a flat roof too, because usually a flat roof is not a timber roof. So the slab roof, you won't have an issue so much with the wind getting underneath that eave and lifting it off. So that's not an issue. I'm talking about pitch roof now, like most of the time it's some timber roof. So you don't want to make it too shallow. The other side of the island, because they don't get the direct impact, it might not be so much of an issue. But on this side here, because we get most of the wind directly, then you would want to consider making your roof a little steeper so the wind will just bounce off and go up like that. It's not going to be enough space to lift from underneath. Then we would also say climatic condition. So in parts of the world, like in the North Pole, you tend to have snow falling. So on top of the roof, you don't want the snow to accumulate. So you want it to just fall off easily. So you would consider making your roof a little steeper, right? So climatic condition could be an issue. We don't have that situation here because our climate is a tropical situation. So that's not an issue for us, but we're looking at general situation. And we would say traditionally, churches tend to have steep roofs, so a tradition could be a factor. We're not saying that the roof of churches must be steep, but traditionally, usually they are like that, and it usually helps with some amount of acoustic and how we place their fixtures inside the building. If you have a pipe organ, they will normally have the pipe extending way up in the air, so you need a lot of room space. for that. So the sound basically will travel within that space. But churches can have flat roof. Nowadays we have churches with all kind of roof, but that's just a tradition. So it's a factor that one could consider. Cost is also a factor. We know that pitch roof, the maintenance on it is going to be higher than a flat roof. So over time you'll have to do some repairs and stuff like that. So it will, person might say, I don't want to spend so much money on that roof. Even in the initial construction, you can have a higher cost, but the maintenance certainly will be higher. So now aesthetics, which has to do with how it looks. So this one right here on the right, a multi-pitch roof. People will think that if a roof has pitch, it looks better than a flat one. Not that a flat roof. You can do things to a flat roof to make it look good too. But if it's just flat alone and there's nothing else about it, then it doesn't look as attractive like when you have roofs that have pitches on them. So aesthetics is a factor. And even what I would say your finish material, the roof covering finish material is also a factor. If I were to draw a steeple, let me just draw a line to say that if that was a steeple and I'm using shingle, wooden shingle or clay tile or whichever, if you were going to make it steep, then you basically can reduce the lap to a shorter distance. But if you are going to make it shallow, then you would have to increase the lap. The reason for that is if the wind is blowing and the rain is falling and the wind is blowing, then you don't want it to push that water up underneath the lap and then it leaks. But if it is steeper, then it will basically not travel so far up unless you have some heavy wind. But you would not just make it very short anyway. But you could reduce on the length of your lap and then you'll be able to use less shingle to cover your roof. But if you're going to make it shallow, then you would have to increase that lap so that you compensate for the leaking. And if it's just one length of zinc, then you basically don't even have to worry about whether it is deep or shallow because you don't have overlap to deal with. So even the finish covering material can influence the the pitch of your roof, whether you make it too steep or shallow. All right, and there are other things I'm sure, but we won't consider much. Now, having said all of that, we are now going to be looking at some typical pitches that we use for roofs, and these are standard pitches now. So we need to be familiar with two terms for now. We call the horizontal distance from the center of the building. So this is the building, from the center here, going towards the wall here, we call that the run distance. And every 12 inches, we would call that the unit run. And the overall height, we would call that the rise. And every increment of whatever rise you're using is what we call the unit rise. Now, full pitch, which is the steepest a roof should ever be, is what we would call a 24 in 12 pitch. So it means that the rise would be 24 inches and the run, which is constant, would be 12 inches. So we would say that that is a full pitch roof. Full pitch roof. So the whole is 24. Now the 12 remains constant. So this distance, which is the 12, would not change. It's the rise that would change, but not the run. The run remains constant. So rise over run. So this is a whole. Now, this is a little small for you to look at. So what I will do is jump to the next slide where we could look at some numbers bigger. But what this is saying is from down here, we have 0, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right up to 24 inches. And you have lines drawing from this point, going at different angles up to those different measurements. So we would just know that a full pitch, which is the hole, is 24 in 12. Let's move to the other slide now where we can zero in a little bit more now on the pitches. Since the other screen was a little tight to look at, this is a zoomed in version of half of it. So 24 is the whole. So 12 in 12 now would be a half pitch roof. Why? 12 is half of 24. Remember, the second figure remains constant. That is the run. It's just the rise that will change. So this is halfway. And basically the angle for that now would be, if you find the tan inverse of that, so the tan inverse of half pitch roof would be 45 degrees. So basically you'll be finding the tan inverse of 1, because we know that ratios are fractions. So 12 in 12 is the same as 1, right? 12 into 12, 1, 12 into 12, 1. So by the time you find the tan inverse of 1, the angle is 45. Now a quarter pitch roof would be 6 in 12, where 6 is a quarter of the 24. So ratios are fractions again. So 6 in 12 is the same as 0.5, a half. Tan inverse of 0.5 is 26.5. So you will say that the angle is 26.5. Normally they just round that off and work with 2070. Now most residential buildings are usually quarter pitch, and if not quarter pitch, most of the time they are 7 in 12, which is approximately 30 degrees. So when you are doing manual drawing and you are using your set square to draw a 30-degree line, you basically were doing a 7 in 12 pitch, where it is 30 degrees. It's 30.5, but most persons just work with 30 degrees. So it's approximately 30.5 exactly. Now, so these are different pitches that could be used for a roof. 1 in 12 going all the way up to 24 in 12. So I just picked a few of them. A 1/3 pitch would be what we call 8 in 12, where 8 is 1/3 of 24. So what you need to remember is that the whole, which is a full pitch, is 24. And what these numbers into 24 will be is what the pitch. So each of them we just say 5 in 12, 6 in 12, 7 in 12, right? But there are a few of them that I use on a regular basis, like quarter pitch, 1/3 pitch, half pitch, and full pitch to a lesser extent. But that's what it means here. Now, what does that mean? Well, basically, for the person who is building the roof, the carpenter, they would need to be using a device or a tool on site to ensure that the roof is at that angle. So let's say we pick quarter pitch, which is 6 in 12, right? Let's say we pick a quarter pitch. Now the carpenter would have to use this tool, which is called a framing square or a builder square, or they could use a roofing square, and there are two different versions of it here. But most of the time they would have a framing square. So I'm going to tell you now how you would get the rafter to be cut so that when it is raised up and put in place, the roof is actually 27 degrees. So you may have seen on a drawing a little triangle, and you see a 6 at the side and a 12 up here. What that means, the pitch of that roof is 6 in 12. All right. Now, in order to get the rafter to be at a 27 degrees, or in imperial 6 in 12, so the degrees is really for metric environment, and the 6 in 12 is really for the imperial environment, because 6 inches and 12 inches. But when we are drawing in metric, we use the degrees, and even in imperial, you can use the degrees when you're drawing in AutoCAD. But they still need to put this 6 in 12 so that the workman on site will understand, because they don't have a protractor out there to work with. Unless they have a roofing square like this, they can measure off those angles. And most of the time, they would have their framing square. So it's important that we still put the 6 and the 12, or whatever the pitch is. So this is how it works. Let me zoom in on this tile. So let's say you're going to be using a 6 in 12 pitch now. what the carpenter will do, they will take their framing square and they line up 6 inches. So they work with one edge of the board, right? So let's say this piece of board is going to be the 2x4 or the 2x6 that they're going to be using as the rafter. Let's say a common rafter to start with. So they would work with one edge of the board. So we're working with the top edge now. So they would line up 6 inches on the framing square and line up 12 inches on the other side. So this would represent the rise and this represent the run remains constant. So they would line up the two of the numbers. Here they have something that they literally lock it in place so it can't shift. But most of the time they don't have that on site. They have to just adjust it until the two numbers line up on the same edge. And then you take a pencil now and mark this edge. And you take a saw and cut that. Let's say we cut that off until it is cut right from end to end. Now, let's imagine that you now take that piece of board and raise it up into the air so that the edge that is cut now is plumb to the ground, like this drawing here. So if you raise the piece of board up in the air until the cut edge, where the 6 inches was, to get it plumbing to the ground, then the angle at which, that's this edge now, the top edge, would now be at 27 degrees. That's how it works. But that plumb cut will not only be at the end of the rafter, where the fascia board would be. You would also have it at two other places. You would have it where the rafter is now sitting on top of the wall plate, which is what we call the bird's mouth cut. It has two different cuts. It has a feet cut, which is the horizontal, and it has a plumb cut, which is the vertical, two of which we now call the bird's mouth. So this plumb cut is also parallel to where the fascia board is, as well as the other place where you'll have a parallel line to that is where the rafter now meets with the ridge board at the top of the roof. So that plumb cut will be those at those three places. Tail of the rafter, where the wall plate is, and at the ridge board. The same principle will occur for other pitches. If it's 18-12, you line up 8 inches with 12 inches, so the 12 would remain constant. So it's just this one that would change. And you would mark again and cut, and by the time you raise it up, it will be at a different angle. Right? So that's how they get the rafters to be at those angles on site. So that's the application of it here. If it's the frame, if it's the roofing square, they would be using this, and they would put it against it like this up here, and then they could cut their plumb cut. So this basically represents where the rafter would be, right? So they would just mark out the seat cut and the plumb cut and cut that out. So it's kind of easier to work with that because you see it happening like how it would be on the thing. But when it's on the ground like this, some people can't really figure it out. So this is basically a 2x4 over here. And how far in this cut goes, basically what they would normally do, let me zoom in over here, is to divide the width of the board, or the depth of the board rather, because this is the vertical part. You wouldn't see the width. So you would divide this into 3 equal parts, and then you would, so let's say I have 3 lines coming down, divide 3 equal lines, like this. So let's say I have 3 lines coming down. 1, 2, 3. Let's say divide it in 3 equal parts, right? You would basically draw the line in until it touch that one, and then come down perpendicular. So you're into 1/3 of the fender. You don't cut all the way in, just about to 1/3. All right. So that's the principle there. All right. So let's move on now, and we will basically say that when it says quarter pitch, it means that the height of the roof, in this case here we have 1/8 for the gable roof, but we're not going to be doing the gable. We're going to be doing the hip one. So I'm going to jump over all of this and go down to where the steps are for the hip roof. So we are doing a hip roof, which is quarter pitch, 16-12, 27 degrees. So when it says quarter pitch, what that means is that the height, let me jump back to a slide so I can just use that rather than sketching on the screen. So if I go back to this one that has this on it. All right, so let's look on this as an example. So this is showing the pitches, right? This is where about where the 16-12 will be. You have a 9 in 12 and 11 in 12 and different pitches shown here. But let's choose one of them. Let's choose a quarter pitch, which is up to here. So what it means is that the height of the roof will be from here to about there. And when we say height, we're talking about from wall plate, where it rests on top of the belt beam, up to the apex of the roof. So quarter pitch means that the height here would now be quarter of your span. So let's say this distance, which is the span, right? Let's say this distance, which is the span, is 30 feet, for argument's sake. Now, your span of the building is the distance from the outside wall to outside wall going across like that. So let's say the span is 30 feet. Right? Let's say it is 30 feet. Then what it means is that the height from where the wall plate is up to the apex will be quarter of that distance, which would be 7 feet 6 inches. So it means that the distance going up to where this would be your 7 feet 6. That's what it is. That's what it means. 7 feet 6 from here to here. So you can have an idea as to what the height of your building is likely to be. Not the building, the roof, before you even construct the roof. Because once you know the span, then you can calculate what the height will be. So quarter pitch means quarter of your span. And the span is the distance from the outside face of the wall to the outside face of the wall where it is on the thing. So the angle basically wouldn't come from out here like what you see here. They just put a triangle on top of it. When you're drawing your first line, you draw it from where the wall meets the belt beam here. So we'd go up like that. So we're going to see those steps coming out. But this was just a triangle on top of the thing, just showing some typical pitches, right? But you actually start working from here at the corner. All right, so let's now look at the steps to draw this roof. All right, so I'm going to jump back over to that slide that had the roof, the steps for the quarter pitch. So we're jumping down to this one. Our first step would be, because we're going to be using 27 degree, is to draw that 27-degree angle on that side. And down here on the other side, for it to be 27 degrees from here, then it has to be 180 degrees minus the 27. So it's actually 153 degrees. So we're going to use the line command, turn off ortho, and use the roof layer and draw those lines. So let's jump back to AutoCAD now, where we'll start that. All right, so back in AutoCAD. So let me change my layer from wall to a roof and turn off my ortho and launch the line command, L enter, or you pick your icon. I'm going to start from this point, which is end point. I'm going to draw a line at an angle. It doesn't matter what angle because I will specify that angle. Let me just type 6,000 on my distance. It could be any length. And then please do not press enter. You press your tab key. It locks that distance in and it now requests the angle, which we are saying is 27 degrees. And you press enter, then escape. Then the other side, you launch the line command again and pull the opposite direction. I'll use 6,000. It could be any distance. If it's too long, we can trim it. If it's too short, we could extend it. 6,000, then I press the tab key, and then the angle this time is 153. And we know how we get that, right? 180 minus the 27. Enter. All right. So I'm going to press escape. So that basically determines the slope of my roof. But we're now going to get the overhang on either side. So what we will do is offset the overhang in our current layer using the steps that we have learned before. So we're offsetting from one layer into another. So it's O for offset, enter. Then L for layer on the offset, enter. And then C for current, enter. And last but not least, The distance now, which is 475 that we use on our roof plan as the overhang, we're using that same distance. So we're going to offset the two span walls. So this one on the left and the other one on the right, both of them. And then to make life easy, instead of extending the line and then trimming, we will just do one thing that can do both at the same time. And that's the fillet command. So if I do F for fillet, enter, and let's double check our radius. Our radius is at 0, which is good. But we're going to do it 3 times, so we need multiples. So that's M, enter. And I'm going to click this line and that line, and you'll notice it cleans up at the top. However, I will do the same at the eave of the roof. So I'm going to click the slope line, but instead of clicking below, which will fillet down, we're going to click above where the intersection would be, and it will fillet up. So it does both at the same time. It extends and trims simultaneously. So I click on the other side, the same thing, slope line and vertical line close to the top. So basically we now have the overhang. Let me press escape. Now we don't need this line anymore. We don't need that line anymore. But let me just jump over to the presentation again, just to explain as to why we're not going to have that line. So we're going back to the presentation, and all the steps that we have just done a while ago is mentioned in the presentation. So when you're doing your elevation, you'll be able to use that as a guide. All right, so the next slide shows what we just did. We offset the overhang on either side, and then we use the fillet to fillet up on both sides. And the reason now why we are going to look at this slide is to explain this step. So the line that we drew first, the 27-degree line, was from here going up. Okay, it was right here. Let me stop back. I think I accidentally went forward. So right here was where we drew the line from, the 27. And then when we offset the overhang and clean up, it came down here. It's just that this has a square cut underneath here. We're not going to put that square cut. We just continue with the line going down. So basically, if you are looking at your roof in elevation, you cannot see through the top of the roof. So you would not see this line at all, because that's the underside of the rafter. What you'll be seeing is the top edge of the roof. So what we are going to do is to move this line up to the top edge, where we would basically see. So there's no need for this line. Likewise, we could not see the top of the wall anymore because the roof comes down over it. So it will be hiding that line. So the line I told you just now that we don't need, we're going to erase that. So we want to know how far up to move that line. We're going to use our fascia as a guide. Our fascia is 200. So although it shows here that the fascia is underneath, we're just going to use it up to the top. Now, when you're doing the detail, you will show here, in more refined way how it is constructed. In elevation, all you're doing is just giving a graphical representation. So we're just going to work with the 200. So what we'll do is just move this line up to the top to say that is where the top face of the roof is. So that will pick up in our next step to say we need to move those two sloping lines only up to the top of the face of the roof by 200, and then we can erase the top of the building line. Afterwards, we will draw horizontal lines after we fillet the corners to clean up to create the fascia board. All right, let's jump back to AutoCAD and those steps will be demonstrated. All right, so now that we're back in AutoCAD, we can select the two lines that we want to move, launch the move command, M enter, turn on your ortho just to ensure that you're basically going vertical and not at an angle. You turn on the ortho and then pull up and type the distance now, which is the 200. Press enter. All right, good. So we are now up to the top edge of the roof, the face that we could see. We can't see underneath. It was very important that we had this line initially because the very first line that we had to draw had to come from that corner. But it's not important anymore, so I will erase that line. We can't see through the roof and see that wall anymore. So I will erase that line. All right, let's clean up here now. So you notice this line went a little higher than it should because when we offset it, it was the same length at the top. So what we're going to do is select, so F, enter, and we're going to do it 2 times, so M for multiple, enter. So slope line and slant line on that side, likewise on this side, sloping line and vertical line. Then we can now draw horizontal line because it's a hip roof. We can see the fascia board going right around the building. So we're going to draw a line from end point at the top here, where the sloping line meets the fascia, all the way to the next side end point, which should be a horizontal line. All right. Likewise, underneath end point, same way, and across to the line coming down end point. Good. So if we can now see the fascia, we would agree the reason why the line had to be erased, because if you can't see the roof, can't see through the roof to see the wall, then that means you don't need that line anymore. Likewise, we would not see this portion of the wall either that is underneath the roof. So I'm setting cutting edges so we can trim the part of the wall above the fascia level there. So PR, enter, and we would need to trim this off on that side. Likewise, on the other side, the same thing. All right, good. So what we're now seeing is the hip end of this portion of the roof. But the other side over here, we will not get the full extent of it for now until we draw the next elevation. So what I'll do is just copy this part of the roof. So I'm selecting from right to left so that only the things that it comes in contact with, which will be the fascia board, vertical fascia, and the sloping line, those 4 lines, launch the copy command, CO, enter, and endpoint here, and then go across to perpendicular on this wall. So we're going to use the perpendicular O snap to determine where to place it. All right, so that's going to give us the slope on that side of the building. However, we need to extend these lines so that the fascia board will basically touch these coming across. So this is sideways, but this is coming at you, right? So this one needs to be extended. So EX, enter, enter, and I'll just extend those 2 lines so that they could meet. So the fascia board round here will come and meet to the fascia board coming this way, which is why that line was drawn. Now the height of this roof, we can't just join it like that, right? And in our next segment, we are going to go in detail as to where that line will end up, but it is not correct to do something like this, to draw a line from there to there and say that is it. Because if you are doing that, which is incorrect, you are saying that the span of this part of the building is the same as the span here, which is not. We know that this part of the building is 7,000 and this part is 6,500 as overall distances. So therefore, we don't expect those two to meet at the same place, right? And if you look at the presentation, which we will talk about in the next segment, we will justify why it is that we need to do one of 2 things to do. All right, we're going to be looking at 2 different approaches. If we are going to just draw the front elevation, what you could do to know where the top of that line should be, as well as if we're going to draw the 2 or 3 or all the elevations, another approach how you could just work itself out, because it's the principle that you would have learned in orthographic projection that you would need to use to get such thing working. All right, so we're almost